Okay, so take two on the right overlay this time, so you can actually see my desktop. Welcome to the Stray Basilisk coding stream. Today we're going to make a cool snowfall simulation of some kind, inspired by the festive patch we put out to Steam Hounds in December. But it's actually going to be a little bit more awesome and cool than this, I think. What we're doing is based on a couple of previous projects, and we're kind of mashing them up and combining these elements we've done before in a different way. So one of these projects is this sand and water kind of simulation we did. This pixely simulation where we have like these sand particles which kind of flutter around and pile up. And I kind of want to do something similar with the snow in our simulation so it can like accumulate like this. And by the way, this is on our GitHub where you can now find a project with, or rather my personal GitHub, Jason M. Davey, where you can find all of our previous projects all in here. Some little previews and descriptions and stuff. So yeah, this is now your one-stop shop for all the code, and after this episode, sometime in the next couple of days, I'll be uploading this code there too. Yeah, so one of the projects we're kind of mashing up is this thing here. The other project is something we did called Smoke and Embers, which created this cool effect where we have this smoke, but what I really want to focus on here is these little particles which are moving around and following like flowy paths through the world. And this is done using like a vector field of perlin noise, which I'll get into and explain later, but I kind of want the snow to follow a kind of similar logic. So ultimately we'll have a scene with snow particles. So, you know, hundreds of these little particles, which will each be following their own little path, which will not be a straight path, but some kind of fluttery, organic, natural seeming path, and they'll kind of somehow move in unison as if they're being blown around and by flights of wind and stuff like that. So these things will fly around, and ultimately they will find themselves settling on scenery. So we're going to have like some pixel art scenery here. So something like a little tree, and when one of these particles hits it, it will implant itself as a little grain of snow, you know, and this snow will like build up, and kind of like the physics we saw in this GIF, it will pile up and then, you know, fall on the ground, pile up down here, and all of that kind of cool fancy stuff. So there's basically two totally separate layers to this. We have this particle flow simulation, and then when it kind of collides with this image, we have this grainy, physicsy thing going on as well. So these will be kind of two totally separate simulations, and there'll be a cool, interesting like interface between these, right? So as soon as one of these particles hits a solid part of the background, then it's going to be converted into that layer, into that world, and it'll become a pixel on that grid, and it's going to have some like certain other physics associated with it. What I'm going to start with is the particle simulation though, I think, and I'm going to be borrowing some of the code we did from this Smoke and Ember simulation, because I've literally written this exact same thing before on a previous stream, which you can go back into the VOD archive and watch. You can go to the GitHub and see the full source code for this, but I'm going to explain everything about how this kind of works as we go along. And also I'm only going to cut out the code we need, so a lot of this stuff can be ignored as it's not going to be totally applicable, and in doing that I'm hoping to kind of go through and explain how like literally all of this works. So basically what we have here is a particle class, and I'm going to start replicating something like this in our new project for Snowfall. So I'm going to add a new tab, particle, so what does the particle have? It has a position and a velocity. I think I'm going to use p vectors for this. Just so it's not literally the same code. And then, yeah, position is just the location where this thing is at, and then the velocity is right now, you know, what kind of direction is it going and how fast. And by updating its position every frame with that velocity, we're kind of going to create this illusion of movement, and this is basically how game physics and particles more or less all work. So we're going to give it a position and velocity. We're going to give it an update function. Some of this stuff I'm missing out for now. Some of this won't be applicable. Some of it, you know, I'll put it back in when it becomes relevant. So what we do typically, yeah, again in game development or game physics specifically when we update something, is we tell it how much time has passed, because if our frame rate is low and the computer is running slowly and it's only doing 10 frames per second, then each frame is going to be a tenth of a second. Whereas if our computer is running at 100 frames a second, each frame is only going to be a hundredth of a second, so each frame it needs to move less if the frame rate is higher, if that makes sense. So this is some stuff to do with acceleration, which I will not do just now, but what I will do is yes, this makes sense for us to do, I think. So we want to give it like a max speed. Let's actually make this factor this out here. I don't know how fast we want this to be, so I'm just going to choose 75 for now again. Let's say if velocity dot x squared is greater than then we want to so what's this saying? So doing something which may appear weird is that we're saying, so first of all, the magnitude of a vector is the length of the vector. So if our velocity, if we take this particle and kind of, let's imagine we're zooming in on it here, so it'll have its position like x and y here, and its velocity is going to be kind of, let's say it's moving down and right, then this is kind of the x component of the velocity, let's say vx, and then this is kind of the y, let's say vy. The magnitude is just the length of this, and you may notice this is like a right angle triangle, or you could, you know, think of it this way. And you use Pythagoras, so you know a squared plus b squared equals c squared to find the length of this, which is the hypotenuse of the triangle. But actually doing a square root on a computer is a relatively expensive thing to do, so rather than saying is the length of this greater than 5, it's equivalent to saying is the squared length of this greater than 25, you know, or 5 squared, which is actually a more efficient comparison to do, which is why you'll very often see, you know, there'll be a convenience function to get the square magnitude because it's cheaper to do. So this is kind of exactly equivalent to this, it's just faster to calculate it. And then if it turns out that we are going too fast, then we're going to do set mag, which ultimately probably will do that square root work and that kind of thing, but we only do it if we need to, pretty much. So if we limit the velocity, put a speed limit on the thing, and then next thing we want to do is basically this. So I'm going to say pos dot so what am I doing here? So you may wonder why I'm doing this component by component. I could have just said pos.add. The reason I don't want to do this is because this will kind of create a new vector object internally. I imagine that's what it's doing. You know, because this we'd have to do, you know, pos is equal to pos.add vel, something like that. Which is very convenient and nice to do, but since this is a real-time thing in Java, this requires allocating a new vector, which, as we'll see shortly when we talk about pooling our particles and efficiently handling up this big batch of all of the particles in the world, you just don't want to allocate stuff like this. So we will do this kind of manually, and just modify position in place, as you would call it, because it's kind of just more efficient. Now, you know, they say premature optimization is the root of all evil, and you shouldn't like optimize things just for the sake of it, I would say, but sometimes it's both of this thing with using the squared magnitude and this thing with doing the component-wise thing are not like creating a new vector and storing it back in the pos variable, are the kinds of things which are just always the right thing to do, and I would just do by default. And I kind of consider this a reasonable, just through experience, this is just a reasonable premature optimization, if you like, because it's just no harder to do than it is the other way, and it's just, you just know it's going to be way better ultimately. So that's that. That's pretty much it, right? So let's now have a draw function going on, and I think all we want to do with draw is, so in here we did some fancy stuff, right? We were actually drawing images for these things. We were tinting them different colors for these like embery things, but we don't need to do any of that. Our particles are going to be little white pixels. So all I'm going to do is say, is draw a rectangle at pos.x, pos.y, and it's going to be 1 by 1. Can I do this with point or something? I think not. I think this is fine. It's drawing a little yellow underline. If you use likely, that's fine. Okay. Oh, I should also do fill white, no stroke. So the code we have here is already relatively simplified from this. That's weird. Oh, you know what? I've got like a drive sync thing going on, which is sometimes messes around with stuff. So let's make sure everything is there and saved. Okay, let's do a quick test of like drawing some of these particles. So in processing, the first thing you do is you create a setup function where first thing you do is create the window by giving it a size. So let's say, what's going to work out? Oh, you know, we're just testing, so let's just put any old random thing in there. You also can set a mode, and P3D is just generally more efficient. I think you can just always use this, more or less. So for now, I'm just going to create a list for these particles. Okay, and then let's just add like 100 of these. Give it a random position on the screen. Let's give it a random 2D vector. There are arguments for this. Let's actually check the documentation here. Random 2D, it's a unit vector, there are no arguments. Okay, cool. So these are going to be going kind of slow. Let's actually scale them. Something like that. Is it scale or is that something wrong? Is it multiply? Okay. Then in our update, let's just do, let's give it a black background for now. And let's say for particle P in particles p.update. Oh, we don't have the delta time Again, that's something I'm going to copy here since it's a very common thing to need to do. Yeah. It's not called update, it's called draw. God, it's been a little while. So all we do is determine how long has passed since the last frame, and we do that by remembering. So this millis function gives us the relatively precise time. Okay, it's not that precise. The relatively precise time at the, like right now, and we just remember what the previous value was, and then actually let's put yeah, we just calculate the difference between the last frame's time and our current time, and then we kind of divide it by 1000 to convert millis into seconds, and then we update this millis last frame with the current time to remember that for next time. So pass that in here, and then let's draw them. I'm actually going to do this separately. I could have done it in the same loop, but I feel like this will be closer to what we ultimately want to do in the future. So let's see what we've got. We cannot see anything. Okay. First of all, let's make these bigger. Still can't see anything. Oh, you know what? I didn't add this, did I? Particles.add p. That would help. Okay, they're just randomly floating around now, but there they are, particles indeed. Let's try putting them back to 1. So actually, so for these snow particles, we are recording their exact position, which may be on like a fraction of a pixel. I mean, obviously they're going to get drawn on one particular pixel. I think we want to do that for the physics stuff. Actually, when they land, they're going to be locked onto a very specific grid. Like if you look at our example here, like these are very much like on a grid. We're not tracking their like position in fractions of a pixel or anything like that. So, you know, that's something that will change at that transition point. But I think we're pretty good with this. So take a look at them now. Okay, they are tiny. So another thing I want to do maybe is just scale up the entire sketch to give it a chunky like pixel art feel. So I may just outright scale everything by, I don't know, 3. Yeah, you know what, let's do, let's not. Let's make this a variable, so final int. Can we do static like that? Okay. Sometimes static stuff is weird because of how processing works. I don't think it works inside these classes. But we can do that. I can do width divided by scale factor, height divided by scale factor. Or what I could even do is create like a separate variable like scene width and height. And then I can sort of calculate those here because I want to avoid like repeated redundant mentions of things. So I'm just going to say scene width is equal to width divided by scale factor, and scene height is equal to height divided by scale factor. So then all of our like logical stuff can be in terms of scene width and scene height rather than the actual window width and height, because our world is going to be at a lower resolution than what we see on the screen basically. So hopefully this does the job still. Oh yeah, okay, of course, okay. Can't be final because we're going to assign to it. Okay, they're looking a little bit more chunky now, and this is Seems reasonable to me for flakes of snow. I think the next thing is to talk about pooling these particles. So right now we just have a list of particles, right? So we can visualize this like, here's a list, and then we have one particle in here, which has its, you know, its position and its velocity. And then we add another one with a position and velocity. And then we add another one, and so on like this. Eventually one of these particles is going to like hit something, and then we're going to be done with it, so we would probably delete that, and then the next particle is going to get added on the end. Kind of like this. And this is okay, it's convenient and it works for us, and we can make it a little bit better by making this a linked list, because linked list makes it relatively nice rather than these things being in an array. You know, they would be kind of like daisy chained together, which means that if a particle in the middle of the list dies, then it's actually relatively easy to like remove it and then just like redirect this link back to this one. So it makes it easy to handle things dying, which are like in the middle of this list. But actually this whole approach of dynamically adding things to the list is like just pretty super inefficient, and it's especially bad with Java because Java's a garbage collected language, and basically if you create lots of tiny little objects which you then throw away, eventually it builds up, and Java kind of stops your whole program for a couple of milliseconds to like clean it all up. And you know, and in like a big, if you're doing like web backend development, that probably doesn't matter too much, but if you're doing a real-time game type application, then that can cause little FPS hitches or commonly like little audio hitches. You just cannot really tolerate that, so you really want to avoid using new to construct loads of little objects which are like temporary and throwaway. So the better thing to do is just to allocate a big old list with enough space for, let's say, you know, however many maximum snowflakes you think you're going to have, like maybe that's 1,000. Then for each one you're going to have the position, the velocity, and then just a little flag saying if it's alive or not, you know, like if it's alive, if it's dead or alive. And then rather than adding things to this list, you simply, the list is already there, it's already full of particles, they're just dormant to begin with, and when I want to create a new one, I just populate the position and velocity and tag it as alive, and then when we do our draw on updates, we only draw and update living particles. When a particle hits the ground, we just mark it as not alive, and then next time we want to spawn a new particle, we just look through the list for like a slot within the inactive particle and reuse it. So it's like a recycled pooling thing, which is pretty much the way to do anything like particles or bullets and things where you need to spawn loads of them. It's just way more efficient to do it that way. So looking at some of this particle system code, we can see that we do something like that here. So let's kind of copy out the relevant bits into our new project. So let's call it particle system. Particle system. It's going to have, it's going to be a class. It's going to have our array of particles. Not even a list, because an array is going to work just fine for this. We're going to give it, I would say init. We can just do this in the constructor actually. Particle system. Let's give it a certain capacity. And then we're going to say, so in this project we try to calculate it based on spawn rate and how long the particles last. In this case we can't really do that because we don't know how long the snowflakes are going to last. I think because they could float around and not hit anything, like forever potentially. So I think what we'll do is we will just spawn them into the scene. Maybe right at the beginning we'll already like populate loads of snowflakes randomly over the screen, and then whenever one lands on the ground we'll just spawn, recycle it back at the top of the screen somewhere. Yeah, so that way there will just always be the same number of particles alive. So let's just give it do this, and then I'm going to say I'm going to actually put a new thing into the list. So I think what we want to do is to just give these by default like an empty vector. And then we need this flag, right? So boolean alive. So it's going to start zeroed out and not alive. It doesn't really matter what these are, because when we really spawn them and activate them, we're going to give them a particular position and velocity anyway. So that's all we need to do. It will already be dormant, and then that's fine. That's all good. The other thing you normally do is you'd keep track of, okay, so let's say we did something like this and we'd added this particle in, then we'd added this particle in. When we go to add the next one, rather than like always starting from the top and looking for an empty slot and then finding one here, we'd normally keep track of, hey, the last particle we added is in like slot 2, so you should probably look here for the next one, the next empty slot. You know, if it doesn't find it, you'd still need to go through the list and loop back around and try and find an empty slot. But I think that in this case, the only time we'll spawn a particle is when a particle dies, and we'll reuse that exact same slot. So I don't even think we need to keep track really of... You know what, I'm beginning to think we don't even need to keep track of whether the particles are alive or not, if we're always going to have the same number in the world. Right, we can really simplify this. So all I'm going to do is say spawn... You don't even need to do this. Okay. Okay, this is going to be way simple. Way, way simple. So we're just going to create them like that. And then I think we could give them... What should we do? I'm thinking about how the interaction with the... what do you call it? With the ground and them sticking, you know, settling, I guess we could call it, on the ground is going to work. But I don't think I won't worry about that right now. I'm just going to give them a random position to begin with. So let's just give it a little respawn method. Let's have the snowflakes themselves know how to respawn themselves. Maybe not totally ideal, and we're just going to use something like this. X is equal to... is equal to just a random value like that. Yeah, this is going to be way minimal code because of these, like, simplifying things. You know, this isn't a general purpose particle system we're making, so you know, it really doesn't need to be. So I'm kind of, I was trying to avoid allocating vectors, and this will do that, but you know what? Okay. Don't need to prefix these. I mean, I could do this dot, but you know. $x times. Yeah, so I'm doing a few things to make this like more like relatively efficient. This is probably the least efficient thing because it's allocating something. I didn't want to bother going through the effort of implementing this myself, which I could do with some like trigonometry and stuff, but it's not super necessary. let's just do it. Let's just see how, let's just show how that's done anyway. Random angle is going to be a random number between 0 and 2 pi. That's the random speed. So what is the x component of this? It is cosine of the random angle. So this is what that random 2D vector is doing internally, I would imagine. Okay, so let's just do that and then have these things respawn themselves. And then I'm going to say if they go off screen, so if pos.x x is less than 0 or pos.x is greater than or equal to scene width. Remember, I can't just use width and height because we're doing some scaling. Y is less than 0 or pos.y is greater than or equal to scene height. Then we're going to respawn. Okay, so ultimately we're going to also do a check to see if it landed and should settle on the ground, but for now it's just to check if it goes off screen, and we're just going to respawn it in a random place. Yeah, maybe in reality we'll want to respawn it like near the top and with a kind of downwards velocity, but as we're just testing the particle layer right now, I think this is okay. So, yes. Let us. I mean, this should just work. So let's give this an update function. All this is going to do is update all of the particles. Yeah, in fact, this is going to be so simple that this class may have been unnecessary entirely, but let's just use it anyway. So we shouldn't construct it until setup runs, because the respawn is going to depend on scene width and height. Hey GD8, thanks so much for the follow, much appreciated. So let's actually construct this like here, like when we were spawning these particles before. Capacity, let's say 1,000. Okay. Let's also give this a draw. Which does a very similar thing. I'm actually loving how simple this particle management is going to be, given these particular constraints here. So what I need to do now is particles.update, pass in the time delta, draw, and then we should now have 1,000 particles always on screen, spawning in with random positions and velocities, and as soon as they go off screen, another random one will respawn, and it will do that by like recycling and just resetting the position of the dead particle. So let's see. I mean, probably what's actually going to happen is this is going to crash because I introduced an error. But no, it seems to be pretty okay. Okay, awesome. So next thing to do, I think, is to have these particles move in a more interesting way, which is again something we can port over from our previous streams project, whereby we have them follow this perlin noise vector field thing. So if you're not familiar with how this works, I will do my best to explain. So perlin noise. Ooh. Perlin noise is something you may be visually familiar with, even if you're not familiar with the tech behind it. It's basically a algorithm developed, I believe, in the 70s by Ken Perlin for generating cloudy-looking, smooth, fluctuating noise. Yeah, it's pretty interesting, right? It's kind of cool still, but I think it's about to get way cooler. Hopefully. So I'm trying to read your username. Koshikutesita. I can speak a bit of Japanese, but I'm really bad at katakana names for some reason. It's Koshiku Desita. Ah, I get it. Okay. Right, yeah. I guess I was right, but it's always hard to make the connection between Koshiku Desita and Gothic Death Eater. Okay, that makes more sense now. Cool. Okay, yeah, let's get this stuff going on. So the cool thing about Perlin Noise is the way, as a user of it, I mean, how it works behind the scenes is pretty crazy complicated and very mathy. And ultimately kind of beyond me to like invent something like Perlin Noise. But as a user of it, it's really nice. Basically, I can say, hey, I'm going to give you an X and a Y coordinate, and it's going to give me a random kind of number. Yeah, I can speak. 会話ができるぐらい喋れるんだ. I lived in Japan for about a year and a half. Yeah, so the cool thing about Perlin Noise is I can just give it an X, Y coordinate and it will give me back a value between 0 and 1, basically. Kind of like you can consider it like a grayscale value, and it has like this smoothness, right? Like it doesn't... Oh, that's cool. Whereabouts did you stay in Japan? So, yeah, so after I graduated, I worked for about 5 years in the corporate IT programming world, and at a certain point I thought, screw this, I'm going to quit and move to Japan for a little while, and I did that whole thing. Minatoku. Oh, that's cool. Yeah, Japan is great. I would love to go back. Like, obviously COVID makes that kind of hard, but I'm kind of pining. It's been a few years now since I was in Japan, and I would really truly love to go back. Yeah, so the cool thing about this is we can use this. Let me copy this. So we can, if you want to generate, basically we can use any of these points to generate a random vector, right? So what we would do is we would say if it's white, let's say it's going to be like this angle. And then if it's kind of a gray, then maybe it's like more this angle, and as it gets darker, it's more kind of this angle. Basically, we can go where from like black to white, mapping from different angles, right? So black is like maybe this kind of angle, and as it gets lighter and lighter, that's like a mid-gray is like this angle, and then if it gets white, it's kind of looped all the way back around. So by sampling the value there, we can generate an angle. And then what that effectively gives us is like for any given point here, really at whatever resolution you want. That's the other cool thing about Perlin Noise. Actually, black and white would be the same, but a mid-gray would be kind of like pointing the other direction. So at any point, we can use this to find different angles, and they like smoothly transition from each other, right? So I think in this previous project, there was a debug view where we could see those. Yeah. So basically you can use it to create smoothly changing like fields of directions. And the other thing is so this is just the 2D bit of noise, but you can also, there's such a thing as like 3D Perlin Noise. Yeah, right, it's kind of like a cube of this stuff. And by taking different slices through that, as time progresses, taking deeper and deeper slices, it basically causes this texture to like smoothly evolve over time, which is what creates this effect of like these things like waving around, which is kind of like the wind changing if you think about it. And we can tweak parameters like the kind of spacing and scaling to make this more or less variation, like across the whole little scene we're building. But this is kind of what I want the snowflakes to kind of follow, as if these arrows, these vectors, are like pushing them in different directions. So I can take some of this code here and do something like this. So let's just say, can I do static? Let's say okay, so limiting velocity. So let's like sample perlin noise to get a random direction. So I think there's just a noise 2D function in processing. Let's look up the reference, or let's just look at my reference right here. Okay, so it's just noise, and you just pass in like an X, Y, and or Z. Let's just do X and Y for now. Pos.x, pos.y. We also need a scale, because, you know, this noise has these fluctuations and hills and valleys at a certain kind of resolution, which may or may not align with the pixels on our world. And actually, I think if you want these smooth undulations, so I'm using something called processing, which is built on top of Java. Basically, it's designed to be very simple to get graphics up and running. You know, it just has all of these built-in like graphics functions, and it's just very nice to use for like quick prototyping. I wouldn't use this for like a full project which I was going to release, but for like creative coding kind of stuff, it's actually really, really useful for that. Let's see what scale we used. Yeah, so what I was kind of saying was that how spread out or closely packed these little hills and valleys are depend on the kind of grid at which you sample this noise. And typically if you're jumping like one whole unit, then that may be like jumping a big amount like over this little world, right? You know, like all the way over here, like from here to here, which means that one pixel will have very little relationship to what's next to it, if that makes sense. So you want nearby pixels to have like similar values, so you probably want to kind of scale or like zoom into this so that a difference of one unit, once you apply that scale, is kind of less. Me on the front page? The front page of what? Of what? Oh, of processing? No. that's Dan Schiffman, who is someone I really look up to and who does similar kind of streams and videos to this. Well, there's a couple of greys in there, maybe. No, Dan's really great. If you check out the Coding Train YouTube channel, it's like really, really amazing, and it's honestly a massive inspiration for what I'm doing here. So big props to Dan. OG, Dan Schiffman. Let's see what kind of noise scale we used. How did I even set that? $20. Yeah, 0.01, something like that. So this means, you know, if we move one pixel over, then we're not going to sample like values 1 and 2 in the noise. We're going to sample like 0.0001 and 0.0002, something like that. Let's do that for now. So that gives us a value. How does processing map it? Is it between, does it give us between 0 and 1? Yeah, there's a whole lot more information about this here. Okay, between 0 and 1. I was wondering if it could have been between like minus 0.5 and 0.5 or something. So it's between 0 and 1. So the angle is going to be, so mapping it from a range between 0 and 1 to a whole angle. This gives us a random angle. Now there's one kind of weird thing about perlin noise, which actually makes sense if you think about it, which is that you'll get very few values which are like close to pure white and very few which are close to pure black, and you get a lot of values which are like mid grays. So if you're, you know, if you consider a value of 0 to be like pointing that way and then like increasing around the circle, a mid gray is like pointing down, and then, you know, it's getting darker until it's black is like the same as white as it loops around. So most of your values will be like biased towards this direction because the noise just inherently is biased towards mid grays. So there are ways to account for this, but I think we generally want the snow to fall downwards. So as long as we rotate this thing so that the bias is towards going down, then it will generally cause the snow to like fall down, which is probably okay for us. So what that means is, by default, if you convert like an angle to a direction, then an angle of 0 is actually points right, and then it goes like counterclockwise, right? So this is pi, and then we kind of want to it's like 3 pi over 2, right? So another 90 degrees. So by default we're going to be biased towards stuff going left. So let's actually just do that, and then we'll kind of just rotate these angles so that it's biased towards going down later on. But we can kind of hopefully demonstrate this effect. So then we can say L.x plus equals, actually use very similar logic to what we did before. So I mean, snow does like, it will sometimes like float up into the air. I mean, there clearly is like gravity. We could also add a gravity force. We'll kind of see. We'll need to tweak this so it like looks and feels right, I think. The realms of quantum. I guess depends how small these particles are, maybe. I mean, they have mass, so gravity must work on them. It's just wind is like the stronger force, I guess, at that point. So times noise, what do we call it? Noise intensity. So this is like acceleration, right? Accelerate the particle in the direction derived from the noise. We should also scale this by time that's passed. Okay. So let's actually give these things a speed of 0 to begin with, so we can purely see the effect of this noise field, and we can tweak some of these parameters. So hopefully we'll see something interesting. mg, yeah. I mean, acceleration is just g. It doesn't matter what your mass is, right? Like, if you weigh 10,000 times more, then gravity pulls on you 10,000 times more strongly, so it all cancels out. So how much you weigh, yeah, it's just g. It's like a certain constant. I mean, in the real world, that's like 9.8 meters per second, but in the context of like this little graphics toy, we just set that to whatever value looks and feels right. So you can clearly see this bias towards moving left, right? So let's... Yeah, okay. So it's like F equals mg. Also F equals ma. Which means that mg is equal to ma, the masses cancel out, meaning acceleration is equal to the gravitational constant, basically. Yeah, this is cool. Like, this works for a particular wind. No, that's fine. Honestly, my physics is not that much greater than A level, and then I got quite into A level maths, so there's stuff I've forgotten, like all of those inclined plane rotating stuff. Like, I'm not 100% on all of that stuff. Okay, so what I think is basically if you see there's some variation, right? It generally moves left, but some things kind of go down, some things kind of go up. So if we just rotate this by 90 degrees, then stuff will generally be falling, which I think we want the snow to do. So let's try that. So I'm just going to plus... I'm just going to add... to bias towards downwards direction. Yeah, so the rotation starts this way. The bias is to like 0.5, which is this way, and then we add another bit to point downwards. I think I've got the math right. This is the kind of thing where I just write what feels right and then run it, and then if I'm did plus instead of minus, I'll just flip it. Yeah, okay. There we go. I think you're right. Okay, so now we're seeing this kind of snow falling. Yeah, it's 90, but it's in radians, right? So it's like 360 is like 2 pi, so pi by 2 is like 90 degrees. Okay, so we're seeing the snow kind of spawn in, and one thing is that the perlin noise field that's underlying this is never changing. So they always follow the same kind of paths. What we can do is have the field change over time by, instead of sampling a 2D coordinate, so we're sampling a coordinate based on the position of the particle. If we had a third one for like time, if you like, then we could have this field smoothly evolve over time, and so they wouldn't fall into the exact same pattern. So let's just do... I'm just going to say float. I bet processing gives us this already. Oh, it's millis, right? It's like millis since the program started, so... Okay. Hey, Maleef, how's it going? No problem, thanks. I appreciate you dropping by. I noticed you were playing FTL a bit earlier. How did that... You were playing FTL, right? How did that go for you? Awesome. Nice one. Nice one. So let's actually have the Type A Mantis cruiser. That's cool. So what's next? What's the next challenge on the docket for you? So I think we want to be able to tweak this timescale to affect how quickly the noise field kind of adapts. So what I'm going to do is just say millis times by that. That seems reasonable. And then when we sample the noise, we also do that in the z-axis, which is kind of like, yeah, if the noise is like a cube, we're first sampling like this, and then we're sampling a slice slightly further in, which is like slightly different, but like smoothly changing over time. So yeah, we'll see. They tended to go in that direction, but now they're moving a bit more left. And as we watch over time, that will sway back and forth, and the snow will kind of have movement. Okay, yeah, this sort of like timescale seems reasonable, right? It's shifting like left to right every few seconds, which kind of feels okay to me. You've got all but the secret ship unlocked. Okay, okay, awesome. So you're just going through, knocking off all of the ships until you can do the secret. That's awesome. Is there anything beyond the secret ship? Is that like, is that end game? Is that the ultimate goal? Okay. So one thing I want to do is tweak how these spawn. Right now they spawn random positions on screen. I kind of want them to spawn maybe like in a box, an invisible box like above the top of the screen. Seems like that would be interesting, and then so they would appear to like come in from the top. Also 1000 is a lot and it's kind of lagging a little bit, so I'm just going to make this a little bit lower. Okay, unlock the secret ship and with everything. Cool. So let's have these things spawn in not something like this, but actually from 0 to minus scene height times 0.5, something like that. Yeah, I think so. And then when... let's actually make these constants up here. So, no, let's not do that. So let's have it... If it's less than 0, then it's actually okay, as long as it's... If it's less than that, so the position kind of on top. So if I was to diagram this out, we have our screen, and now they're going to be spawning in a box like roughly like here, and then we only want to kill a snowflake if it ends up like not just outside of the screen but outside of this like entire box here, because they're obviously going to be outside of the screen as soon as we spawn them. We don't want them to immediately die. We want to allow them to exist in this little space up here. You know, maybe we also want to allow them to exist like slightly outside the bounds, like to the left and right, because that would allow snowflakes to like come in from the side. We'll see how it looks. Actually, let me just do that now. Give it a bit of leeway. Need more GPUs. Yeah. Okay, that was interesting. So you can kind of clearly see them following their little paths now. Is obviously a little bit weird. Oh, you know what? Maybe this doesn't like those parameters being the wrong way around, so they're all spawning literally right on the top. Cool! Take your time to chill, Malieve, and I'll catch you back. Catch you back next time. Hopefully you can join us for another stream. Okay, so this stuff is coming in. We don't have enough particles to like keep the screen like somewhat full. So let's just ramp up that number a little bit. Maybe 500. I think over time, as they get less in sync with each other, then it may cause them to be a bit more uniformly distributed. Yeah, right, like over time they're getting more like a continuous sort of flow, if you like. Or what we could do actually is have their initial spawning behavior and respawning be like a little bit different. So we could have them always respawn right at the top. Or, you know, close to it. This could be interesting, so... I wonder if that noise intensity is a little bit too much. You know what I might do is give them a bit of gravity and then have the noise be like a less of a, not the only factor controlling how they move. So, I don't know, something like that. And then I can say, like this, and then I probably don't need to do this anymore. So it's going to be biased to like one direction, but that'll feel like the wind. Yeah, feel like the wind's blowing in a certain direction. I can probably give them a bit of an initial downwards velocity. Plus okay, that left bias is too much, so let's give it like kind of downwards, but not totally. It's also not do this maybe. I don't think we actually need that. The random angle was kind of for that initial testing, so let's instead do something simpler like this. And let us also give them like slightly wider bounds in which they can spawn. You know, what might be interesting is to have the... I'm just fiddling now, sorry. What might be interesting is to actually have this pointing up. So we have the gravity. We can tune the gravity so that they're generally going to be going downwards rather than back up. So that's clearly... The noise is a bit too strong there. So we can make the gravity more intense. So then they'll be more inclined to like flow around a little bit. And kind of circulate and swirl. Yeah, that's a bit too random. Let's just try one. More fiddling. Okay, that's a bit too much, but we're more in the ballpark now, I think. What I kind of want, yeah, is, yeah, this feels a bit nicer. This seems a bit more snow-like, so generally down, but they can somehow... Theoretically, they might move up sometimes, or at least kind of swirl around side to side. Okay, I think for just the snow layer, this is fine to begin with. We can now think about having this snow settle. So, first things first is I need some kind of scene for this to work in. This box is probably reasonable, so what was the size here? 600, so this was actually 200 by 200. I'm going to pull up some assets from our game. So from this winter graveyardy stage we had, and we can try and assemble some of this into a scene here. So let me just pull out, open a bunch of these layers. We can try and cobble together some little scene, pixel arty scene from these. That's kind of a nice background. So what we have in this scene is this kind of stuff, which I think works well. That's like a bottom layer. So let's first... it needs to be 200 by 200, so I can just crop this somehow. Looking at the bottom where the size is. 200. I think. This should work just fine for us. Okay, and then, so this can actually be the background, which I should probably export separately. So, go into our snowfall thing. So in processing, you put stuff in a data folder. I'm just going to call this background.png. I think that should be just fine. I'm going to take some of this other stuff and try to like overlay it. So let's have some of this stuff going on. I'm not a fan of the super tall tree there, it looks kind of weird to me, so let's do this. There were other layers, I think. Although, you know what, maybe this is all we need. Like, maybe bump this up a bit so the ground level is slightly higher. Honestly, this is pretty great. I think this works just fine, so I'm going to make it transparent like this. Let's export this as, let's call it scenery. So let's now just get these things loaded. Scenery image, let's load these in. And this is why I like processing, because this is just super easy to do. I can just load an image and then I can just draw it like this. So I can draw the background image at 0, 0, or the top left corner at 0, 0. Oh, I can then draw our scenery image on top. And it's actually load image, sorry. Get these in. I didn't want the scale to happen. Okay, this is annoying. So it's being scaled with some like smoothing going on, which I really do not want to happen. Seems looking kind of cool. How do I disable smoothing? I think I've done this before and it's kind of fiddly. Or you have to get into like an internal setting. This is where processing is not great, is when you really need to push the boundaries of what you're doing with it. And for whatever reason, changing the scaling filter mode is not something it likes to do. So let me try and remember which project we did this in. Something where we had pixel art and we scaled stuff. We could try and Google it. So what we basically want to set is like the scaling, texture filtering scaling mode to nearest. How can we change this? So this is something very common if you're dealing with pixel art in game dev, is that you don't want it. It's kind of like in Photoshop, right? If I scale this with linear to 600 by 600, then it's going to be like a blurry mess. What I actually want is to scale it with none, or nearest neighbor is kind of what it would be called in OpenGL, or which is, I guess, what processing uses under the hood. You get the chunky thing where each pixel is now several pixels, but there's no like smoothing going on. So we want to basically set the equivalent setting in our processing sketch. So I could have just pre-scaled this image, but I actually want to use the pixel data directly to find like collisions and stuff. So that's probably not something we can do. So let's find out. Let's see if this works. Like, this is kind of weird undocumented stuff you don't want to have to do, but nearest. Ooh, it's not going to like that. Yeah. So GL nearest. So I need to find the raw value for this. really hate doing this kind of stuff on stream. It's kind of hacky. Is it 0? Oop. Unknown texture filtering mode. Okay, let's try something else. Let's go through these until it looks right. Nope. Yeah, look at that. We got it. It worked. So now this has been nicely chunkily scaled up for us. Giving us nice chunky pixel art. Yeah, maybe there's something I'm missing. There probably is a way to do it, but this will work for now. So what I now want to do is something like, okay, so we have our particles in this world, and they have a certain position. Oh. And they're moving, and they're moving, and they're moving. What I kind of want to do is say, if you reach a point where maybe one of your neighbors is white, then you should settle, and you should become a white pixel, like in this image, if that makes sense. And then I'm actually going to write directly into the image like a white pixel. I think that's the way I'm going to do this. The next phase will be having some physics apply, so this white pixel might like move down and fall and settle down here and stuff, but that's something we can look to as a next step. One thing I do want to do is, I think that some of these pixels may not be pure white, and they've got some transparency, which is going to mess with things, so I kind of just want to clean that up somewhat. So I'm going to use this curves tool to say anything that's nearly white should just be pure white. And in alpha, anything that's like anywhere near full alpha should just be like full alpha. So I think that will give us, okay, that's not great. So let's try and make sure we get this pixel here. So alpha 0 can stay at 0. You can be, okay, cool. Now this should be pure white, I believe. Yep, 100% white. So awesome. So what I want to do is, here's the Siri image. So if we're going to be reading the pixels of this, we need to call actually probably want to do this later now. Okay. Siri image.load pixels dot save pixels dot what was it? There's something to basically load pixels and make sure the pixels are loaded into just an array which we can directly access and fiddle with. And then there's something else we call to update pixels. Okay. To like write that back so that, you know, this is dealing with if this texture has been handed over to the graphics card, we need to get it back and actually get the pixels in somewhere our CPU can get at them, and then we need to push it back to the graphics card here, which is kind of what happens there. So hopefully this doesn't crash anything. May slow things down a bit. Okay, seems good. So that now gives us the ability within here to sample some of these pixels. So I'm going to say First of all, we only want to do this if we're really within bounds of the image, because I don't want stuff getting stuck like to the side here, because we're going to build up clumps of snow like on the edge, which is going to just start behaving really weirdly, and it's just not going to work, or we're going to have to deal with like other boundary conditions. So 0 and pos.x less than scene. This is going to be very similar to check to what we had above, but it's going to be strictly checking us against the scene. I'm going to create a little utility called something like is like this. So I'm going to say if x less than 0 or x is greater than or equal to scenery image dot width, or y is less than 0, or y is greater than or equal to scenery image dot height. Then return false because we're out of bounds. Otherwise, we're going to return something like is the alpha of, actually, how is this stored? Scenery image.pixels. Not sure if the colors are packed into like 1 integer per pixel or if it's like 4 integers per pixel. So let's look in here. And then there's pixels. Oh, these are the pixels of the color data type. They raise the size of the image. Okay, cool. So processing has this funny little color data type, which is actually just a number, or an alias for int. X plus y times width. So this is a way, given that these are stored in a 1D array, this is how you map from the XY coordinates to the position in the array. If you're not familiar with this, we've done this on many streams. This is like one of the most common like game dev image manipulation formulas you ever deal with. But that's how we look up the pixel. I'm just going to say alpha pixel is greater than 0. So this will extract the alpha component from that color, and then we're just going to say if it's not transparent, then we assume there's a pixel there. So what I'm going to do here is say something like this: if any of our bring pixels in a settle. Okay, so let's actually do around. So remember, our position of our particle can be fractional. We're tracking it in like subpixels, so we want to round that off. I'm going to say if is scenery pixel set, and I'm going to check I guess for each pixel I'm going to check probably the 8 pixels around it, something like that. Actually, we could probably check the pixel itself. There's possible issues if the pixels move, if the snow's moving really fast, it might be here one frame and then like here the next, and it might settle like here. So that's something we might have to deal with, but for now I'm just gonna do something like this. Okay. x1. Let's say x of equals -1. What I'm doing is creating, just using these loops to go through the indexes of like, so if this is our pixel in question, we've got like x -1, y -1, x, y -1, we've got x +1, y -1, right? Like these pixels in the immediate area around it, we're just kind of enumerating those with a little loop that covers all those 9 pixels, so I don't have to write out the same thing loads of times. So if x of y plus y of, so if that's the case, then we're going to settle, which means stop. Equals just white. And then let's return because we're done settling. Okay. Oh, and then respawn. So this pixel was, this snow is going to reappear somewhere else. Okay. Is this going to work? We shall see. Oh. Okay, something odd is happening there. Oh, that shouldn't be width, it should be scenery image width. So what we were seeing here kind of makes sense actually, which is that they were settling like a third of the way down. And that's because we were sampling into the texture with a wrong offset because we weren't accounting for like the scale of the scene. So this pixel was actually like 1-3 times further through the image or something like that. That's kind of what I imagine happened there. Let us try again now. Bloop, bloop. Oh yeah, this is cool. Basically, as long as our snow doesn't move too fast, then it's not going to like slam its way through. Okay, something weird is happening here. And then something odd is there. Okay, so let's do this actually, because it may be that the rounding put us the wrong side of the edge of the image. Okay. So we'll probably still see some flakes like floating in and then like popping in like this, or yeah, that's still happening. That's not a huge deal really. So we probably only want to set this if there is not already something in this tile, right? So if we should be an integer, shouldn't you? Okay. So what we're doing is we're just doing a double check here that if the pixel is empty. So what I think could happen is that, so say we've got our, let's choose a different color. So we've got our snowflake. It's moving like that. Be small, please. So we've got our snowflake, and it's kind of moving. Oh, what is going on with this? If I don't put it exactly on a pixel, it acts weirdly. So, you know, maybe it ends up exactly here. In this case, we do want to destroy it, but we don't want to turn this into snow because it's already like ground. So I think that's the edge case which we now have covered, which should also prevent that weird accumulation down the sides of the image, I believe. So, snow is falling. Snow is settling on the ground. This is very cool. Awesome. We are very close. There is only one more thing which I really want to do here, which is to apply a bit of physics to the snow so that it can drop. And the frame rate's actually not too bad either. If we made this really big, it might get worse, but for now this is actually okay. Right, it's building interesting patterns, and in fact, something like this could be used as like maybe even like a snowflake generator kind of project, like having particles accumulate like this. Interestingly enough, but what we really want to do is have this snow collapse. This isn't Minecraft where you can have blocks like randomly floating. So let's look to do something pretty much like we did in this project, which will achieve that same thing for us. Basically the way this works is a very simple like cellular automata kind of thing. Basically what it does is it goes through every pixel, and then it says if this pixel's filled and but like the pixel immediately below it isn't, then it can just like move itself down. Or if the pixel would, like, you know, this sort of situation, like let's say this was free, then it will allow itself to, like, if one of them like down to the left or right is filled, then it will kind of also pop down like that. And this will create like a cascading effect of like moving snow. So we can implement something like that. So it's probably going to be another whole pass. So let's have snow, settled snow physics. Hopefully it made sense. It's basically going through every pixel and then looking if there's free space for it to move sort of down into. The only thing you need to be wary about is you're going to like iterate through this whole image, right? Like generally top to bottom. And what you might do is you might move this down. Oh. You might move this down and then continue iterating along this row. Come along to this row, come to this pixel, say, oh, there's space for it to move down into, and then move it down. Continue along this row, come back to here, and basically in one frame this thing will like teleport all the way down to the ground. So I think what we can do is if we iterate from the... Basically we never want to move a pixel twice in one frame. Like if it's falling through the air, then it should just fall through the air like frame by frame. But I think if we iterate from the bottom up, then we won't have that issue. Yes, I think that will work for us, which makes this again way easier than it would otherwise have been, which is awesome. So y is equal to scene height -1. That's not let. I did a bit of JavaScript recently. Y is greater than 0 minus y. And then we can just go left to right because this stuff never moves like this, so we wouldn't have an issue of like, you know, having this like move to the right and then reprocess that pixel twice. It was actually more complicated in this simulation because we have water which can like spread out left and right. So it meant we had to track which particles or pixels had already been updated this frame like in a more explicit way, because things could move in all different directions, up, down, left, and right. But I think because stuff is strictly moving down, if we iterate from bottom up, we should be good to go. So x equals 0, x is less than scene width plus x from bottom up to avoid so what we want to do is first check the pixel immediately below us, right? So if we want similar logic to this, except so this defaults to returning false if it's out of bounds. I think we want something more like can snow flow into, and then if it's out of bounds, then we're going to return false, and then in this case we want to return at equal to 0, right? So if it's out of bounds, we can't flow into it, but we can flow into an empty tile, meaning a tile with, or a pixel with no alpha. So yeah, okay, this is kind of ugly, but it sort of works. So if can snow flow into, well, first of all, we want to check if this is a snow pixel, right? So if if color is equal to white, we can even just do snow. If can snow flow into x, y plus 1, then we want it to, we kind of want to move it down. So all we want to do is set hey podcast show, how's it going? Great to see you back again. I'm going to give you a quick update on what we are doing and what we have achieved. So we're building a kind of snowy scene. If you've been lurking for a while and you've seen this, then do let me know. But basically what we have is these particles, and these are flowing according to a bit of gravity and some noise, which causes a bit of flow and perturbation to create some kind of wind-like effect. Now we have something going on where when they touch a pixel in this this ground image, which is filled, then they despawn as a particle and fill in that pixel and then respawn back at the top of the screen, if that makes sense. So it creates this settling snow. The issue we have now is that they stack up and like the snow never collapses, so it just forms these weird tendrils wherever it lands, right? So we want to have some physics to the snow, and the kind of physics we're implementing is, oh, sorry, 1 second. We're implementing physics whereby if you have a bit of snow with like empty space underneath it, then it will like move down. And that will cause these structures to collapse, and it'll be more like a pile of snow on the ground, which is a bit more the behavior we want. Although that's kind of cool, the little weird tendrily things it forms right now. The way we do that is a bit of logic where we kind of iterate up from the bottom of the screen, and then we say if we found snow here, then, and the pixel below us is empty, then we're going to like move into it. So let's actually do color, snow color equals color. I'll just make this global. Nature of Code. Oh yeah, awesome. Yeah. I mean, I've watched pretty much all the videos for that. I never read the book. I think it's the same content, but yeah, it's very, very cool. So y+1 equals snow color. Let's also do like, this is going to be kind of weird, but like air color. It's just going to be 0, like a 0 alpha thing of some kind. Doesn't matter what the color is, because we won't see it anyway. So pixel below us becomes snow, pixel where we are becomes air. And there's probably elsewhere where we have done this check. I'm just going to say snow color. Ooh. Doesn't like that. Okay, let's see if this will stop stacking up quite so much. Yeah, right, we're seeing some of the snow. If I kind of zoom in here, it'll like drop and then like fall down. So this almost does what we need. I think whether we'd want the snow to also flow out left and right, it will prevent, that will prevent like stacks, like vertical stacks of snow, which we may still get with this, right? But yeah, we're definitely seeing some like vertical spiky stack stuff going on due to the nature of this, when we could have that snow even itself out a little bit more. So I've got 2 different like magnifying programs running at once, which can cause some weird stuff. Okay, let's say else if so one thing is I could check. So right now the snow, a snow pixel can go straight down. What we also want is for a snow pixel to be able to go like down and left or down and right. So it'll do that kind of thing. So one little quirk is if we always check the down and left direction first, then there'll be a kind of bias to how the snow stacks up and how it like forms mounds, which is ultimately what this is going to do. So what I really want to do is to have a random coin toss to see whether I should try and flow down and left first or down and right first, because otherwise, you know, this would always go like that way when really we want it to like randomly go one way or the other, because it will look, it may create some weird visual like artifacts if we don't do that. So let's do something like this. So I'm going to say int. Cool. So if random okay, what we've done here is we picked a direction randomly, so we've done a 50% chance for this to be -1, meaning left, or +1, meaning right. So then the second direction to check can just be the opposite of that. And now we can do something like if can can actually copy something similar. Yes, we use perlin noise indeed. So what we did is, there's actually another project we did, which is a kind of better example, or it has a little debug visualization which will help, which is using perlin noise to create a set of smoothly changing like directions, which you then use to like steer these particles around. And it's really evident here, but we did something similar for the snow. And the code is just like, given the particle's position, we can pull out a noise value, which is just a value between 0 and 1, and then we can convert that to an angle between 0 and 360, and then we can just push the particle in that direction. So as it moves, it's hitting different values in the noise space, and then it's causing it to like be pushed around in different directions, which is very awesome. So let's do y plus first direction. No, so it's actually, it's always y plus 1. It's x plus first direction. Else we can try the second direction. I think this will work for us. So down and yeah, perlin noise is really, really amazing, and Dan Schiffman has some great content on perlin noise. Oh, that was that was awesome. Let me set the frame rate really low so we can see that happen. Frame rate 1 frame per second. But something kind of cool happened there. Just that all of this existing snow like collapsed. Ah, I see what's happening. It's because these trees have so if I print screen that. Whoa. Wow, that was mega zoomed. So it's because these trees have little diagonal going on with this selection tool? Right, basically it can always like fit through this crack. So if I was to fill that in instead, then we would see that the snow would like stay up on these. So I don't know whether we are okay with that. You know, if I do this tree like that, then we should see, get rid of this red junk. We may want to do a check to stop it fitting through cracks like that, basically. So export the scenery image. Now if I play it again, we should see on that one tree that I tweaked that it's staying there. Yeah, like up here, right? So, I think a bit of logic to prevent it slipping through these cracks would be something like it can only move down and right if this square and this one are free, right? So it can't like go through a diagonal like that. It would, this one would have to be empty as well. That seems like it might behave a bit more as we'd kind of expect and hope it to. Something weird's going on with my... Okay, that's what's going on. Let me export that again. So let's do that check as well. So if we can flow like down in that direction, and we can flow just straight up in that direction, like left or right, but not down. So that should prevent us from slipping through cracks, and then I can set the frame rate back, unlimit the frame rate, and then are we done? Is this it? Is this success? Is this what success looks like? I think it may be. So the snow is piling up. It's kind of falling off the trees. Let's zoom in a little bit on a section here. Yeah, this is cool. Sometimes it looks like it's kind of skating around a little bit as it like shoots down the side of things, but this is cool. It's definitely piling up in a snow pile kind of fashion, right? So one other thing we did, I think, in the previous, it's cool, right? Like this is really awesome. So I don't know if you can tell, but yeah, the snow definitely like skates down really fast. So one thing we can do to make that a bit slower, and it's actually what we did with, again, with like the way the sand moves through the water here, is that we would only have the snow move like with a certain probability, right? So right now every frame, if you can move it immediately, like does, and it causes it to like really quickly skate down the sides of the trees. So let's do if, let's actually make it a little constant to float. We're going to call this snow flow rate, and we'll just make it 0.25, something like that. And I'm going to say if random between 0 and 1 is less than snow. Yeah, so basically you load an image. So you load an image, you have a p-image type, and you can load an image just like this. And then an image has an array inside it called .pixels. One thing you need to do though is, if you're going to access these pixels directly, you need to first call this load pixels function to tell processing I need direct access to these pixels. And then when you're done reading or updating them, you need to call this update pixels at the end. And that's just to do with how the data is like stored on the graphics card versus your RAM and when your CPU can access it and stuff. But yeah, you can directly access pixels. It's just a 1D array. You can get an X and Y using this little formula. Yeah, this basically takes the X and Y coordinates and converts it to like the 1D just coordinate in this pixels array. Then it gives you back basically an integer, or processing has this color, which is actually just an integer with like all the red, green, blue, and alpha like packed into it. And then you can use handy functions like, okay, here, so we're pulling a color value out of an image, and then we're using the alpha function to check specifically the alpha component of that color. And there's also red, green, and blue functions, so we could check the redness of a pixel and so on. Yeah. Snow flow rate. So this basically says, you know, before we decide to move a pixel, there'll be a random chance of just not doing it, which will... Yeah, no problem, no problem. Anything you want to ask about, I'm more than happy to go into. So this will slow the flow rate down by just randomly sometimes not updating any given pixel. And if we look at that, we should see, hopefully, a bit more of a sedate... Yeah, look at them. Now more calmly, like, dropping down. Yeah, which I think is more what we might expect from snow. I mean, it's randomness, right? It's not... We could keep track of each pixel, like how long ago it's moved, and do that in a more accurate way, but I think this is fine. Okay, yes, this is great. I love this. I I think we're done for the code. So the last thing is that I maybe want to just try some other images. Because it would just be fun to like draw some other scenery. So some random stuff like this. Call this scenery 2. Don't want to lose the nice one there. Actually, I probably also want to make sure. So this doesn't really play well with like the little bits of transparency we're seeing here, so I'm just going to remove those. To give it hard pixelated edges. Okay. Yeah, exactly. So the logic of the snow is, so for there's two phases, right? So in the first phase, the snow is like a particle, and it's just moving around according to physics, you know. So it has a position, it has a velocity vector, and it will just move along according to its velocity, like frame by frame. Just like that, just happily moving around. And what it does is every frame it checks, and the snow, by the way, is actually only 1 pixel big, so it's not going to look like that. It's going to look like a single pixel. So as it's moving along, it checks every frame. Are any of my neighboring pixels in the scenery layer, which is kind of a separate layer, like filled in? And then as soon as they are, like here, right, it's going to say, oh, my I've got a neighboring pixel that's filled in, so I'm going to delete that particle, basically, and then I'm actually going to paint a white pixel into the image. And then there's a separate phase where now this is the white pixel in the image. We then, after all the particles are updated, we scan through the image for white pixels, and basically if a white pixel has a space below it, then we allow it to like move down, which causes the like physics of the snow like settling like that. So to kind of quickly skip through the code, we update all of these particles, and when each particle updates, it says it uses this perlin noise to kind of push itself in different directions. It applies a bit of gravity. If it goes out of bounds, it respawns itself back at the top of the screen. And then if we touch the ground, then it will settle. And this basically says, looks in a little 3x3 area around it. And if any of the pixels are set, and this just reads into that scenery image, then it will just set a white pixel in that image. And then also respawn itself. And then we do a second phase where we kind of go through the image, bottom to top, check every pixel. And if we find a white pixel, a snow-colored pixel, then we check the pixel below it and the pixels like to the bottom right and bottom left of it, and it will move into one of those if they're empty. And that's, so there's two, the particles and the like settled snow are basically two totally separate things. And when a particle detects that it's close to the ground, it like creates a new snow pixel in the image and then respawns itself as a particle at the top. So these are two like separate layers, if you like. So it's kind of like a multi-layered simulation. Okay, we can kind of see this settling here. We can see the snow rolling off. Oh, this is fun. You know, one thing that might be kind of interesting is if a bit of snow then finds itself like not touching the ground anymore, like these, should they turn back into particles? That's a, I guess we'll call that an exercise for the reader to look into. Yeah, this is really cool how they're hitting the top and then spreading out to form these little piles. It's exactly how I hoped this would work out. So I'm pretty pleased with this. This is awesome. Yeah, this is great. So also thanks to Mr. PhD, who unfortunately isn't here today. We now have a GitHub repository. So I'll put the link in the chat. But you can get the source code to every stream that we've ever done. There's a couple of GIFs and examples. So this particular one is kind of a mashup of this thing we did, which is that pixel falling behavior, and this other kind of particle-y thing we did here. It's kind of combining those two things together. Yeah. Yeah, I mean, I think we call this done. Look at it. I kind of wish I could like shake this and have everything shake around. That might be a cool little exercise. So realize that now shaking a window like minimizes everything else, which is a feature I never use and sometimes catches me out. Yeah, so I mean, I think we're done with this. I'll probably post the code to that GitHub within, you know, sometime in the next week or so before the next stream. Yeah, I think we're good to go. This was awesome. We did this in about 2 hours. The click button. Oh, yes. We could totally do that. Yeah, I mean, these, one thing I think I'm noticing is as there's more snow, it slows down because it's having to trying to process the physics for all of these snow, which is gradually accumulating. So it is kind of getting a little bit, the frame rate's dropping a little bit. You could optimize that, but that would be kind of tricky and difficult. Yeah, I mean, I'm really pleased with this. Like this, this is pretty great, and you could extend it in a few ways. But it's just nice to look at, right? I like these little graphical toys and things that we put together. Yeah, I guess thanks everyone who tuned in. I will drop. Let's see if our bot will work. Ah, come on, there we go. So you can follow us in various places. So on our Twitter, we actually run a regular poll on what subjects to do. So, you know, this is what was voted for. So if you're interested, you can follow us there. And then normally every Wednesday, like the day before these streams, we will post up a poll about things to do. Or you can find us on Discord. You can just message me on there with other suggestions, which I'll then add to the poll. I'm entirely happy to do that. Or if the suggestion's really good, I might just do it, to be honest. Yeah, if you're interested in the main game that we're working on called Steamhounds, it's this turn-based tactical steampunky game. We have a Steam page up and you can see more cool GIFs and stuff on our Twitter or Discord in relation to that. Cool, I think we will probably call it there as our snow is piling up and up. Oh, we're getting this interesting like void. Maybe the contrast is low, but that is actually the background we're seeing through there. Yeah, I guess thanks so much everyone for tuning in, and throw in your suggestions for what stream we do next week, and I will catch you next time. Bye-bye everyone.